Bismillahirrahmanirrahim. Linearization of nonlinear ODEs by symmetries. By symmetries. Okay, so we we take this example from the famous book of Hans Stipney, differential equation, their solution using symmetries. This is non-linear second order differential equation, so we want to solve it using symmetries and linearize it. So let's start from, you see, y double dash is equal to x minus y dash cube. This admit the generator x is equal to partial by partial x plus partial by partial y. So it admit this. If we operate second extension, but second extension is this is not extendable generator on both sides, so on both sides we will get 0. So this is the Lie symmetry generator. Lie symmetry generator. Okay, we will use it to linearize it. So we will do two things: reduce order, number 2, solve it, and number 3, linearize it. Okay, so we have to find coordinate t and s which satisfy these two equations. So from here you see, when we operate, t is a function, t and s are function of x and y. Generally both are dependent on x and y. So when I operate this operator on t, we have tx plus ty is equal to 0, and the other one st plus sx plus sy is equal to 1. So we have to solve these two first order partial differential equation. So the characteristic equation is dx1 and dy1 and dt0. So solving these are two equations. So solving this first equation, that will give me x is equal to y plus some t. So this is x minus y is equal to t. Okay, now solving this one, this is dx1 dy1 and ds1. So solving this equation, this is y is equal to s. This one will give me s is equal to x, but for time being I am taking, so that is the second choice, but I am taking this choice. Y is equal to S and t is equal to x minus y. From here we see that if y is equal to s, then x is equal to t plus s. Putting y is equal to s. So we want to take x to be this and y to be s. So x is t. Okay. Now I have to find y dash. Y dash is dy, which is a function of t and s, and dx, which is also a function of t and s. And for time being, I am taking s to be a function of time, is depend on t. So see, this is the total differential. It will give me y t dt plus ys ds and xt dt plus xs ds. It can be written as yt plus ys is dash xt xs is dash. From here yt is 0 and ys is 1. And from here xt is 1 and xs is 1. Okay, putting the values, over here, this is equal to yt is 0 and ys is 1. So it is s by yt is 1 and xs is 1, so this is x dash. Now we need y double dash. In fact, we will put it here. What are we doing? We are going to put it in s and t. We are going to put this equation in t and s coordinates using these equations. So s double dash is dy dash, which is a function of generally t, s and s dash, and dx, which is a function of t and s as before. So from here, using this concept, this is y dash t plus y dash s dash plus y dash s dash is double dash and divided by xt xs is dash. We see that there is no t and s in y dash, so we will, this is 0, this is 0, because in y dash there is no t and s. So from here we put 0 for this, 0 for this, so we will have something for this. And the denominator is as above here, that is 1 plus s dash. So let's do the calculation. Y double dash is equal to, this is 0 0, and differentiating this, let me do it here, y dash s dash is equal to 1 plus s dash, and the derivative of s dash is 1, minus s dash, and the derivative of the denominator is 1, because derivative of 1 is 0 and s dash is 1, so that is s dash square. So these will cancel. So this is 1 over 1 plus s dash square, and I will put this over here because these two are 0, so only one term is left, and that is 1 over 1 plus s dash square s double dash. This is s double dash, and it is divided by 1 plus s dash, a is before here. So this is equal to s double dash over 1 plus s dash cube. This is y double dash. So now we know y double dash, y dash, y and x. So all of them will be put over here. So I am doing this over here. You see, y double dash is equal to x minus y dash cube. So put all of them. Y double dash is equal to this value, that is s double dash over 1 plus s dash cube is equal to x minus y. X minus y is t, and y dash is 1 over 1 plus s dash, oh not 1 over, this is s dash, so s dash cube over 1 plus s dash cube, that is y dash cube. Okay, so this denominator will cancel with the denominator, and we get the equation is double dash is equal to t s dash cube. So this is the equation in the s and t form. Okay, now y double dash is equal to x minus y dash cube. In the new coordinate, it is s double dash is equal to t n s dash cube. Now reduction of order. Number one, we said that we will reduce the order. Reduce order. For that, let s dash be z. That implies double dash be z dash. So put this the new variable in this equation, that will implies s double dash is z dash is equal to t and z cube. So this is the order of the equation is second, but now this is in first order, the order reduce. Now we are going to solve this differential equation. So this is dz over z cube is equal to t dt. So this is separable equation. Integrating it using the power rule over here, that is minus z minus 2 by 2, and is equal to t square by 2, and I'm taking the constant to be minus c by 2, minus c square, let's say. That is an integration constant I take, and for some reason this will implies that 1 over z square is equal to t square minus c square. No, this is minus t square plus c square, because minus multiply the equation with minus sign. This is plus, minus, and plus. So from here I can write that z square is equal to 1 over c square minus t square, and that implies that z is equal to 1 over c square minus t square under the root. I am taking the positive root. There are two roots, positive and negative, but I am taking the positive one. Now that is z, but we know that z is equal to s dash. So this is s dash is equal to 1 over c square minus t square under the root. So again we have to integrate it. So this is ds is equal to dt and c square minus t square under root. After integration, this will give me s is equal to sine inverse t over c and plus another constant. So this is the solution in the t and s coordinate, t by c plus some c1. But we know that y is equal to s and x is equal to t plus s. So I need the t, so that is t, and it implies that x minus y is equal to t. This is t and this is s. So replace s by y is equal to sine inverse x minus y over c, that is the argument of the sine inverse, and plus c1. So this is the solution in the original coordinate. This is the solution of this equation, and you can check it, but I'm not going into the to check it that whether it is solution or not, but I'm confident that this is the solution. But okay, this is this can be written as sine y, not sine y minus c1. Okay, subtracting c1 from y and then apply the sine on both sides. So this is sine y minus c1 is equal to x minus y by c. Why I'm doing it? For some purpose, and I will tell you later. So this is x minus y is equal to c sine y minus c1, and x is equal to y plus c sine y minus c1. This is my final solution of the given differential equation. This is the solution of this differential equation, and I take this form for reason. So what we did, we reduced the order and we solve it. You see, solution. This is solution of the original. Okay, we solve it. But you see, this reduce. Okay, this transform form is not linear. This is not linear. S dash cube is there. This is not linear, and our video is on linearization. So in this process, we reduce the order and we solve it. Two things are fulfilled, but one remains. This is not linear. I need the linear form. So in the previous case, I take that S is, but this is not linear. I am interested in the linearization of this equation. So now I want to take T as dependent and S as independent. Okay. Now I want this case. T is a function of S. So in that case, y dash will be ys plus yt t dash. Following the t dash, following the step of the previous slides, and s plus xt t dash, where y is equal to s and x is equal to t plus s. So yt is 0 and ys is 1, xt is 1, xs is 1. Okay, so putting that values, yt is 0, so this term is 0 and I get only 1 over here, and xs is 1 and xt is 1, so this is 1 t dash. So that is y dash. Now y double dash is equal to dy dash dx, but this is a function of t s n is t dash and s, because I am taking I'm taking t to be dependent and s independent. So s, t and t dash, that will give me y dash s plus y dash t dash plus y dash t dash t double dash divided by xs xt t dash. Put in the value. This is 0 because y dash is not dependent on t and s. So with respect to s derivative and t derivative, let's do it over here. Y dash t is 0 because no t is involved in this expression. Y dash s is 0 and y dash is dash y dash t dash. Y dash t dash give me minus 1 over 1 plus t dash square. So this term is 0, this is 0, and this will give me minus 1 over 1 plus t dash square t double dash, and this is 1, s is 1, xt is 1, so t dash. So this is overall minus t double dash over 1 plus t dash square, not square, cube. Now putting these value in the original equation, y double dash is equal to x minus y dash cube. So this implies y double dash is minus t double dash over 1 plus t dash cube is equal to x minus y, that is t, and y dash is this, so that is 1 over 1 plus t dash cube. So this is cancelled out. So what we left with, that is t double dash plus t equal to 0. This is linear. This is linear equation, and it is for the simple harmonic motion equation, spring mass system equation. Okay, the solution of this differential equation is t is equal to C1 cos S plus C2 sin S, and putting these information of x and y, we have t is equal to x minus y, and s is equal to y. So x is equal to y plus c1 cos y c2 sin y. So this is the solution of the original differential equation, and we previously find the solution there, which is this one. X is equal to y plus c sin y minus c1. So these two solutions are exactly the same, is equivalent solution. Why I write the previous solution in this form? They are the same thing. These two solutions are equivalent. So in this case, I take S to be dependent on T. And in this case, I take the reverse, T depend on S. But what is better? It is T depend on S because it give me a linear differential equation. This choice give me non-linear soluble. This choice give me non-linear soluble, and this give me linear. So what the symmetry method do? It do three things with ODEs. Number one, it reduce order. If you have a Lie symmetry generator, you can reduce order. Number two, you can solve. And number three, linearize. So that is for ODEs. Either you reduce, the reduction of order is if you have a Lie symmetry generator, you will reduce the order. There is no doubt in the reduction of order. Whether you will succeed to solve or not, that is a question mark, and linearization also a question mark. But the reduction of order, there is no doubt in the reduction of order if you have a Lie symmetry generator. So we did these three things in this video. We reduced the order, we solve the given nonlinear differential equation, and we linearize it. Okay, thank you. If you learned something, then like, comments, and subscribe. Thank you.